Hello, welcome to the second lecture on recursion trees. In this lecture, we will be discussing how to use recursion trees to analyze the recursive algorithms or finding time complexities of those algorithms. So let us quickly recap what is a recursion tree. Recursion tree is a visual representation of recursive calls in a recursive algorithm where we create a node for each recursive call and an edge for each call that is made from one function to another function. So in the previous lecture, we have discussed how to visualize the flow of execution and how to find the return values of the functions by propagating upwards. And in this lecture we will be discussing how to find the time complexities. So why to use recursive trees for finding time complexities? Because the recursive tree shows all the function calls in the execution of the recursive algorithms, and knowing the time complexity of each function call, we can calculate the total time complexity. So what are the basic steps in finding or in analyzing the time complexity of recursive algorithms by using recursion trees? First step is draw the recursion tree and explicitly show the non-recursive work. And second step is determine the cost for each node. For each function call, find the time taken for non-recursive operations. And once you know the cost per node and the number of nodes in that level, we can calculate the cost per level. And we can, depending on the number of recursive steps required to reach from a root to the leaves, we can find out the number of levels. Once we know the number of levels and the cost for each level, we can calculate the total cost. The total cost gives you the total time complexity. In some cases, maybe the base cases also adds a significant contribution. In that case, we need to add the cost of the base cases also. So we will see later, like this is very helpful in divide and conquer also, in analyzing divide and conquer algorithms. So let us try to understand with examples. The first one is, let us take a factorial. So consider this recursion tree for a factorial of n. Now factorial of n calls factorial of n minus 1, factorial of n minus 1 calls factorial of n minus 2, so on. Where you get a base case, you have factorial of 0, that is 1. So now what is the cost at each node? And for each function call, we have we have a constant number of operations, and at each level we have only one node, and the number of levels is, and in each recursive step we are decrementing by 1, so the number of levels is n. So number of levels is n, and at each level we require constant number, that is order of 1, so the total time complexity is order of m. So that's about the factorial. And next let us discuss with the Fibonacci, nth Fibonacci number. For a nth Fibonacci number, let us try to understand with a call of Fibonacci of 5. So Fibonacci of n has two calls, Fibonacci of n minus 1 and Fibonacci of n minus 2. So the cost at each node is order of 1. In the first level it is order of 1, and in the second level there are 2 nodes in the level and each requires order of 1, so 2 into order of 1. In the third level we have 4 nodes, because all previous nodes might be calling 2 functions, so we have 4 into order of 1, and in the next level we get 8 into order of 1, and each time it is decremented by 1, so the number of levels is n, and at each at those leaves we have the cost as 2 power n into order of 1. So when you add up, you will get the time complexity order of 2 power n. So, and you can see that at a depth k we have roughly 2 power k calls, and each requires order of 1, so order of 2 power k. For as we have n levels, so approximately order of 2 power n. Okay. And next, so let us consider a question from GATE 2025. Find the time complexity where we have T of n as 2 into Tn minus 1. There are 2 subproblems, each of size n minus 1, and a non-recursive part is taking n into 2 power n time. Okay, so let us draw a recursion tree. So when you draw this recursion tree, so it has 2 subproblems of size n minus 1, n minus 1, and the work at node at root, that is n into 2 power n. In the first level, the work at a node is n minus 1 into 2 power n minus 1. There are 2 such nodes, so we will get n minus 1 into 2 power n. Similarly, at level 2 we will be having 4 nodes, and each requiring n minus 2 into 2 power n minus 2, so we will get n minus 2 into 2 power n. Okay, so now at a level k we have 2 power k into n minus k into 2 power n minus k. That is, 2 power k is the number of nodes, and each node requires a cost n minus k into 2 power n minus k. So the total cost is n minus k into 2 power n, and there are n levels, because in each step we are decrementing by 1. It has to start from n and it has to reach to 0. So there are n levels. So we get summation n minus k into 2 power n on 0 to n minus 1. So we can see at each level, when you take at a k depth, we have 2 power k nodes, and each node requiring n minus k into 2 power n minus k work. So the total work is n minus k into 2 power n. And at a base case where or at leaves, that is at a depth n, we have 2 power n. So 2 power n cases, so order of 2 power n. So the number of levels is n minus 1, or number of levels is n, and each level requires n minus k into 2 power n. When you sum it up, then you are going to get something like this, which is 2 power n into sum of n natural numbers. that is 2 power n into n plus 1 by 2, so that you will get T of n as order of n square to n. And you know that the leaf cost is order of 2 power n, which is the lower order term. So the answer is T of n is order of n square 2 power n. Okay, so let us see how this is useful, how it is useful even in solving recurrence relations which are of the form and in the divide and conquer. So in case of divide and conquer, we divide the problem into A subproblems, each of size n by b, and the cost required for division as well as for merging is f of n. Okay, so now we can see the recursion tree. So where we have in the first level A childs are there, or A subproblems are there, and in the second level we have A square subproblems. At a ith level we will be having A power I subproblems, and each subproblem of size n by b power I. Okay, and so and the depth is because in each iteration step you are dividing by n by b. At, let us suppose, at some depth d you have n by b power d equal to 1, so that is nothing but n by b power d equal to 1. That is where you get the base case. So from there d is log n base b, so you get a depth as n by log base b, and there you have a power k subproblems, that is a power log n base b, so you have n power log a base b. Okay, so we will discuss this in next part of the video.